Hello students, and welcome to this sixth lecture of heat transfer course EEAQ 3235. Today we are going to have a look at transient heat conduction in semi-infinite solids. Now let us first of all discuss what an infinite solid is, or what a semi-infinite solid is. A solid that extends itself infinitely in all directions is called an infinite solid. So we have a solid here that is extending itself infinitely in all directions. So if the same infinite solid is cut into two, as shown in the diagram, into two at the middle with a plane, then each half, this half and that half, each half is called a semi-infinite solid. In this semi-infinite solid, there is a position, this position here, whereby the effects of heating or cooling that is done at the surface there is not felt at all. At that point, the temperature remains a constant. Now, if we wanted to know the rate of heat transfer, Q, then we would use the Fourier's equation, minus Ka dt by dx. But we are dealing with a case whereby the temperature distribution is a variable with a time. So our temperature T is varying with x and also with time. So how can we use this equation when the temperature is also varying with time? We can only do it by evaluating our dt by dx at that position, because at that position the temperature does not change. It remains a constant. Alright? So it is not varying with a time. So bearing that in mind, let us go now to the heat equation. We have our heat equation, di 2T by di x squared is equals to 1 over alpha dt by dt. This is the heat equation for non-steady conduction with no heat generation. And as you can see, our temperature T, capital T, is varying with a distance x and also with time t. And because of that reason, it becomes very, very difficult to solve this second order partial derivative. So what do? We can try to solve this equation by introducing what we call a dummy variable And using this dummy variable, we can try and reduce this second order differential equation with two variables into a second order differential equation with one variable. So we'll have a look at that side of the equation first and deal with it, and come back later and deal with this side of the equation. So let us deal with di 2 t by di x squared. So we're saying di t by di x is the same as di t by di eta times di eta by di x. And we're saying we're introducing eta here to make this equation an equation with only one variable, and the one variable will be eta, and eta is equals to 1, it is equals to x divided by 4 alpha t to the power of a half. So di eta by di x is equals to, differentiating this with respect to x, we'll get 1 divided by 4 alpha t to the power of a half, such that now di t by di x is equals to 1 over 4 alpha t to the power of a half times di t by di eta. Now di 2t by di x squared is differentiating again this expression above here, and that is equals to the same as d by d eta of di t by di x di eta by di x. This is di, such that if you look keenly at the equation, that can cancel out with that, then we are left with di x, and di x of di t by di x becomes di squared t by di x squared. So that is that. So we have this is equals to di eta into bracket di x is what we have above here, this one here. So that is what we'll plug in this part of the equation. So we'll have that as 1 over 4 alpha t to the power of a half dot t dot eta, and then we have dot eta by dot x. So we can take a dot d eta inside there, so we'll have this is equals to 1 over 4 alpha t to the power of a half, and then this becomes dot squared t by dot eta squared, and then dot eta by dot x, and we saw that this is equals to 1 over 4 alpha t to the power of a half. And you can see that this reduces to 1 over 4 alpha t dot squared t by dot eta squared. So that is what we have for our dot squared t by dot x squared. And note that, and note that. So let us analyze dot t by dot t. So we are analyzing now dot t by dot t, that one there. And we know that dot t by dot t is equals to dot t by dot eta times dot eta over dot t. So we have eta is equals to x over 4 alpha t to the power of a half, which is the same as x for alpha t raised to the power of a negative half. And if you differentiate it with respect to time, d eta with dt, you'll get this remains a constant, x for alpha to the power of a negative half remains a constant, and then we'll have the derivative of t raised to the power of negative half will give us negative half, and then t raised to the power of negative 3 over 2. And this is equals to minus x over 2 for alpha to the power of a half, this is 4, times t times t to the power of a half, and we have dt by dot eta. So this is the same as minus x over 2. I'll take t to the power of a half inside here. That is, I'll take that inside here so that I get into bracket 4 alpha t to the power of a half times a t, and that is di t by di eta. So this is equals to minus x over 2t 4 alpha t to the power of a half di t di. So we can go back to our heat equation. So our heat equation, and we say that di squared t by di x squared, that is di squared t by di x squared is equals to 1 over alpha di t by di t. And we've seen that di t squared by di x squared is 1 over 4 alpha t. Di squared t by di eta squared, which is equals to the right hand side of the equation, which we have found to be 1 over alpha x over 2t 4 alpha t raised to the power of a half di t by di eta. So these, we put right terms together, we get di squared t by di eta squared is equals to, there is an alpha here, okay, it is there, alpha 4 alpha t, this one here, if you bring it there, we'll have 4 alpha t divided by 2 alpha t, which is 2. So we'll have 2 somewhere up here. So we'll have 2. And then we'll have x divided by 4 alpha t raised to the power of a half dot t by dot eta. And as you can see, and there is a negative sign, x over this, x over 4 alpha t square root is the same as eta, so that is eta, and we have 2 dot t by dot eta. And now, as you can see, we have a second order differential equation that we have kept as a partial differential equation throughout. But as you can see, we have only one variable, that is t is varying with eta. So we can write this expression as d 2t by d eta squared is equals to minus 2 eta dt by d eta. So that is our resulting differential equation, second order, and as you can see, it has only one variable, that is t is varying with only eta, and that makes it solvable using the usual tools we have for solving differential equations. So now, after coming up with that solvable equation conditions, so let us have a look at, and we're saying that at that t at eta is equals to infinity, we have t being equal to t naught, it is equals to, no, it is equals to not infinity but 0. We have t naught, and when x is equals to infinity, at t is equals to 0, that's when we have our eta is equals to infinity, and t as eta approaches infinity is what we have denoted by our ti, t subscript I. The differential equation can be solved by using the d operators method. Solve it by separating variables. So we have a d squared at t by d eta squared is equals to minus 2 eta dt by d eta. It can be written as d eta of a d t by d eta, which is equals to minus 2 eta dt by d eta. So you can see we have dt d eta here, dt d eta there. Okay, dt d eta, dt d eta. So we can put this as d, this d here, dt by d eta, that is that d dt by d eta, and we bring this down here, divided by dt by d eta. Okay, and then we take d eta to the other side, so we'll have minus 2 eta d eta. So now I recall that in general, when you have a dx over x and you integrate it, you get ln all on x. So let us integrate this equation here, equation 2. So integrating 2, we'll get ln of a dt by d eta is equals to minus eta squared plus a constant of integration that we'll call c1. So we can say that d eta or dt by d eta is equals to e raised to the power of minus eta plus c1. This is the same as, we can put it here, is the same as e raised to the power of minus eta times e raised to the power of c1, e raised to the power of c1, e raised to the power of c1. So e raised to the power of c1. Well, this was a squared, this was sorry, this was raised to the power of, okay, so this is a squared, and that is squared. And note that e raised to the power of c1 is equals to another constant that we can denote by just c. So dt by d eta is equals to c times e raised to the power of eta squared. Let us integrate again. We'll have a dt integral is equals to an integral of c e raised to the power of eta squared d eta. And when you integrate dt, you'll get t, and this becomes is equals to integral of e raised to the power of eta squared d eta plus a constant of integration. Let us call it a c2. So let us apply the boundary conditions. So at t is equals to 0, eta is equals to 0, and t is equals to t naught. So plugging back into our equation, we have t naught is equals to c integral of 0 to eta d eta, because eta raised to the power of 0 is equals to 1 plus now our constant of integration c2. And then at t is equals to so this becomes a t naught, that is this above equation. T naught is equals to c eta plus c2, right? That is by integrating d eta. So we can rub out this. T naught minus c2 over c is equals to, over eta is equals to our c. So now let us go to our boundary conditions 2, whereby we had t eta is equals to infinity, t is equals to ti. So plugging back into our equation, we have ti is equals to the integral of c raised to the power times e raised to the power of that squared d eta plus c2, and e raised to the power of eta squared, and eta is infinity, becomes 0. So all of that is saying e raised to the power of that, and that now is infinity, becomes 0, such that the whole of this is equals to 0. So it implies that c2 is equals to ti. So now we have our equation in general. T is equals to c, and the c is equals to t naught minus C2, and we've seen that C2 is Ti divided by eta, integral of e raised to the power of eta squared d eta plus Ti. So we have a T minus a Ti. Alright, that is, going back to our equation here, T minus Ti divided by T naught minus Ti, T minus Ti over T naught minus Ti is equals to 1 over eta times the integral of d eta. So let us have a look at the Gaussian error function, and the error function of x over 2 root of alpha t is also called the error function of z, which is equals to 2 over the square root of pi times the integral from 0 to z. So this is 0 to eta, 0 to z of e minus eta squared d eta. And you can see the similarity between the Gaussian error function, right, and our equation up here. So we can say that T minus Ti divided by T naught minus Ti is equals to the error function of z, where z is equals to x over 2 alpha t, or if you like, you can take 2 inside there. So this becomes square root of 4 alpha t. So that is our error function. And we have tabulated values of error functions in our mathematical tables. So you need only the mathematical tables to solve an equation in semi-infinite solids. And let us have a look now at the temperature distribution, and not the temperature distribution, but the rate of heat flow per unit area, which is given by minus k dt by dx. And we said makes things very easy when we evaluate it at x is equals to 0. So this is the same as minus k d eta, the error function of eta times d eta by dx evaluated at eta is equals to 0. So this is equals to k T naught minus Ti 2 over pi to the power of a half e raised to the power of minus eta squared over 4 alpha t evaluated at eta is equals to 0. And this will give you a result that is q is equals to k t naught minus ti, because when t is equals to 0 this becomes infinity, and e raised to the power of minus infinity becomes 0. So divided by pi alpha t, all of that to the power of a half, t minus ti divided by t naught minus ti is equals to error function of eta or z. Now t minus ti is equals to t naught minus ti into bracket error function of eta. Now we can say that t is equals to ti plus t naught minus ti error function of eta. But dt by dx, which we need somewhere else, is equals to dt by d eta times d eta over dx. And you can recall that this here, this one, that is d eta by dx is equals to 1 over the square root of 4 alpha t. So now let's have a look at dt by d eta. That is the same as d eta of t, and t is equals to ti plus t naught minus ti error function of eta. And that definitely will give us d eta of ti is 0, because ti is a constant, so we'll have t naught minus ti d eta of the error function of eta. So now that will give us t naught minus ti d eta. As you can remember, our error function of eta is 2 over root of pi times the integral of e minus eta squared d eta. So this is the same as t naught minus ti times 2 over root of pi times differentiating an integral, you just recover the integrand itself. So we recover e minus eta squared, and we're multiplying okay, that is our dt now by d eta. So now we have our dt by dx is equals to 2 t naught minus ti over root of pi times e minus eta squared times 1 over 4 alpha t square root. So this is equals to 2 t naught minus ti over square root of pi e minus eta squared. This is the same as 1 over 2 square root of alpha t, and 2 cancels out, so we're left with dt by dx is equals to, I can put root of pi and root of alpha t together, so I'll get t naught minus ti divided by the square root of pi alpha t times e raised to the power of eta squared. And we said, because we are saying that q is equals to minus k dt by dx, so q is equals to minus k t naught minus ti over the square root of pi alpha t times a raised to the power of negative eta squared, and we say that this should be evaluated at x is equals to 0. But we said when we were looking at the boundary condition, when x is equals to 0, eta is also equals to 0. So q is equals to minus k t naught minus ti over the square root of pi alpha t times e raised to the power of 0, which is equals to 1. So that gives us our heat rate equation. So now, after coming up with our equation, we are now armed to handle any question. We have an example here that reads, a steel ingot, very large in size, is heated to 745 degrees C, and it is to be hardened, quenching it in a bath of oil at 20 degrees. So you're told to determine the temperature required, not the temperature but the determine the time required for the temperature to reach 595 degrees C at a depth of 12 millimeters. So the ingot may be approximated as a flat plate. So we're saying from our equation T minus Ti over T naught minus Ti is equals to error function of x over 2 square root of alpha t. That is equals to error function of a z. So we have 595, that is the time that we require, the temperature that we require, minus the temperature of the surroundings, is equals to the initial temperature 745 minus 20, and that is equals to 0.79. So from the tables you find that at 0.79 the error function, no, z is equals to 0.9. So we have now 0.9 is equals to x over the square root of 4 alpha t, or 0.9 squared is equals to x squared over 4 alpha t. So 0.81 is equals to 12 times 10 to the power of negative 3 divided by 4 times 1.2 times 10 to the power of negative 5 times t. From this you'll get t is equals to 3.7 seconds. Now we have another example, example 2, that reads a 60 millimeters thick mild steel having diffusivity alpha is equals to 1.22 times 10 to the power of negative 5 meters squared per second is initially at 30 degrees C, and you're told that it is suddenly exposed to the surroundings on one side of a fluid, which causes the surface temperature to increase to and remain 110 degrees C. You're told to determine A, the minimum time that the slab can be treated as an infinite body. B, the temperature at the center of the slab 1.5 minutes after the change in surface temperature. Now note, for a solid to be considered semi-infinite, this is semi-infinite, the following conditions must be observed, i.e. L divided by 2 square root of alpha t is greater or equal to 0.5. So squaring both sides, we get L squared over 4 alpha t is greater or equal to 0.25. our L, which is 0.06 squared divided by 4 times alpha 1.22 times 10 to the power of -5 times 0.25 times t, that must be greater or equal to 0.25. So you see T minimum is equals to 295.1 seconds. B, at the center of the slab, x is equals to 0.03. So T minus Ti over T naught minus Ti is equals to error function of Z. So T is equals to Ti plus a T naught minus Ti error function of Z. Error function of Z is equals to 0.03 divided by 2 times the square root of 1.22 times 10 to the power of -5 times t, and t is 1.5 times 60, which is 90. All right, and that gives us the error function of 0.453. This is error function of that. So error function of 0.453 is approximately equal to 0.47. That is from the tables. So T is equals to 110 plus 0.47 times 30 minus 110, and that will give us a figure of about 72.4 degrees C. And that brings us to the end of the 6th lecture. Let us join again for the 7th lecture. Thanks.